We're going to be looking at sequences more this section, and basically what we want to know is whether a sequence converges or diverges. Well, remember what a sequence is. So for this particular sequence, we want to take the limit and we want to figure out, does it converge or diverge? Now, when we're talking about the limit of a sequence, we also have to talk about limit laws, and so some of this will be a little bit of a review. Now, a sequence is a list of numbers that follow a particular pattern. So one example of a sequence would be the sequence a sub n equals 0 to infinity. So that means I start with n 0 and I go up one step, 1, n equal 1, n equal 2, all the way up toward infinity. And so this one has a specific definition of 1 over n plus 2, n equals 0 to infinity. So what this looks like when I write it out would be n equals 0 would be 0 plus 2 is 2 in the denominator, so 1/2. N equal 1, 1 plus 2 is 3 in the denominator, and I think that you see the pattern here. So 1/5, 1/6, 1/7, etc. So this, in the curly braces, is my sequence. Now there's a couple interesting characteristics about this particular sequence. First of all, they're all positive terms. That doesn't happen for all sequences, but it's worth noting. Also, we can look at this and we can see that it's constantly decreasing. It's getting smaller and smaller with each term. And this is important as well. Now, just because it's constantly decreasing doesn't mean that it will converge, but it's an interesting characteristic that we should consider when we're determining that. Now, because it's constantly decreasing, we call this monotonic decreasing because the behavior is constant, hence the word monotonic, and it's always decreasing. It's never increasing and it's never staying the same. Now, also, this term on the left, that's bounded above, or sorry, below. So that means it's the lowest that it goes. And then what we want to think about is we want to think about, okay, what is this bounded above by? Now we don't know because this goes off toward infinity. But I can see that this is going to get smaller and smaller as n increases. So I'd have 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000. The overall fraction is going towards 0 there. So I could say that this is bounded by 0 as well. And I'm going to switch these around. I'm going to call this one above because it's a higher number, even though it's on the left. And then bounded below by 0 up here. So those are some interesting characteristics. Now, once I know all of these characteristics, I should be able to start talking about the idea of a limit to figure out this bounded above or below piece. So I want to be able to take the limit of this, but this is not a continuous function. I have integer values. I'm plugging in n equal 1, n equal 2, n equal 3. I'm not plugging in 1, 1.1, 1.11, etc. So there's a theorem that basically states that if I take the limit of integer values as they approach infinity of some function, the theorem takes over and says you could do the same limit and treat n integer as a continuous set of values. So we're going to change it to x for all real numbers between negative and positive infinity of the same function, but I'm replacing n with x to show that I have that continuous idea of this function. Now this limit is equal to 0, and you might say, well, why is that? And that's because it's one of my shortcut rules. If I take limits at infinity, if the degree in the numerator is less than the degree in the denominator, the limit is 0. So if we're going to use this idea a lot, these shortcut rules, so we'll review those in a second, make sure you always write down why you get 0. You always want to support your conclusion with this statement right here. So what I can say then is therefore, the 3 dots in the shape of a triangle means therefore, the sequence converges because it's going towards 0 and it's bounded and it's monotonic. Now monotonic increasing, monotonic decreasing. Monotonic's the important word here. It has that same behavior and it's decreasing. So therefore the sequence converges and its limit is 0. Now graphically, let's see what this looks like. 1 over n plus 2. So 1/2. I started with 1/2. And that is when I plugged in n equals 0. So here it starts right up here. And then when I plug in n equal 1, I had 1/3. And n equal 2, I had 1/4. And so we can see that this behavior, that this limit is going towards 0. Now this is not a solid line because remember these are integer values, so that's why these are plotted as individual points. Now let's go ahead and review those limit rules that I was talking about, those 3 limit laws, and these show up a lot. So you probably already have these memorized, but let's go ahead and give them a quick review. So this is for limits at infinity. These are our shortcut rules. So first of all, let's take the limit as n approaches infinity of the sequence 4n cubed over 2n cubed plus 4. So what I can do here is apply that theorem that allows me to take this from integer values to continuous values from the real number system and compare that. And if it's true for real numbers as x approaches infinity, it's also going to be true for the integer values as well. So this would be 4x cubed over 2x cubed plus 4. Now this limit is going to be 4 over 2, which equals 2. Now why is that? Because the degree in the numerator equals the degree in the denominator. So again, you have to support your conclusion. How did you get this limit? If the degree in the numerator and the degree in the denominator are the same, the limit is the ratio of those leading coefficients. They're not always what's in front. It's what's in front of the highest power. So that's one of my shortcuts to my limits rules. The next one, let's look at the limit as n approaches infinity of 5n squared over 12n to the 5th minus 7. So again, I can apply that theorem that takes it from my integer values to real number values of x. So I have 12x cubed minus 7 in the denominator and 5x squared in the numerator. Well, this limit is equal to 0. Why is that? Because the degree in the numerator is less than the degree in the denominator. That's our shortcut rule. So make sure, again, you include this justification for your solution. Okay, so we've looked at equal powers, we looked at less than in the numerator, so now let's go ahead and look at greater than in the numerator. So the limit as n approaches infinity of 2n to the 5th all over n minus 1. So what we're doing here is we're trying to figure out what the terms of these sequences are doing. So the terms of the sequence that we just looked up here, they were getting smaller and smaller and smaller and going towards 0. So that's the information that's providing me. The terms of this sequence were going toward 2. The terms of this sequence were going towards 0, and the terms of this last one will be going toward infinity. Again, I apply that theorem, and I take the limit as x approaches infinity then of 2x to the 5th all over x minus 1, and that's equal to infinity. That means they're getting larger and larger and larger. And this is because the degree in the numerator is greater than the degree in the denominator. So those are my shortcut rules. And if we look at these one more time, you can see that the top two converge. They go toward a particular value. So this converges. This one converges because it's going to 0. And then this last one, it's not going toward a particular value, it's going toward infinity. So what I would say here is that this last one diverges. It's getting larger and larger and larger, and it's not going toward any particular value. We're going to do one other problem for a quick review, and this is when we have an indeterminate form for a limit. Of course, we know how to use L'Hopital's, but there's one that shows up quite a bit in this section, so I want to make sure we review it. let's go ahead and look at the limit. And again, what I'm looking at here are what are the terms of the sequence doing. The terms of the sequence again are n equal 1, 2, 3 integer values, and my function that I'm plugging that into is n minus 2 over n to the n. So there's lots of n's here. So again, that theorem allows me to take this and rewrite it in terms of a real number. And so then I have x minus 2 over x to the x. So if I take this limit, in the numerator and the denominator I have equal powers. So what would end up happening here is the limit would be the ratio of the leading coefficients in the parentheses, so that would be 1 over 1, which is 1. And then the exponent would be 1 to the infinity. Well, you'd think 1 to the infinity would be 1, but it's actually indeterminate. And indeterminate means, I don't know, it could go converge or diverge, but I have to do more work to figure that out. So the more work that we're going to do is we're going to kind of use natural log so I can get this exponent out. So what we'll do first is we will simplify this and rewrite it a little bit. I'm going to split the numerator into two pieces. You can always do that. You can never split the denominator if there's two or more terms. And what I'd have here then is the limit as x approaches infinity. X over x is 1 minus 2 over x to the x. And still, I get 1 to the infinity, and that's indeterminate. And indeterminate means to do more work. So the more work that I'm going to do is I'm going to go ahead and set the solution equal to y for this. So I have y equals the limit as x approaches infinity of 1 minus 2 over x to the x. Now I'm going to use natural log, so I'm going to take the natural log of both sides, and the reason we do that is we want to bring this exponent out front, so then I can use the properties of logs to do that. So I have the natural log of the limit as x approaches infinity of 1 minus 2 over x all to the x. So the idea here is the log of the limit is the limit of the logs. So I can pull the limit out front. And again, we drag along the left-hand side here. So I have the limit as x approaches infinity, and then I can pull this x out front that's in the exponent. So I can pull that out front of the log. So I have x natural log 1 minus 2 over x. Now if I take my limit now, this first term right here, that would go toward infinity. And then this term right here goes to 1 in the parentheses, and the natural log of 1 is 0. And infinity times 0, again, I'm going to have to keep working. It's still another indeterminate form. So I'm making some progress, I think, but it's still indeterminate. And so indeterminate means I need to keep working at this. So what I'm going to do is I'm going to rewrite this so I can get it into a L'Hopital's form. Now, if you want it in a L'Hopital's form, you need a numerator and a denominator. So I have the limit here as x approaches infinity. And this x that's out front, I can take that and I can rewrite it as 1 over x in the denominator, because when you divide by a fraction, you multiply by the reciprocal. So if I multiply by the reciprocal of 1 over x, that's the same as multiplying by x. So that is a rewrite. So I'm taking x in the numerator and I'm rewriting that as 1 over x in the denominator. Now in the numerator, I still have the natural log of 1 minus 2 over x. Okay, so now if I take my limit, 1 over x as x goes toward infinity is 0. And of course in the numerator, 2 over x as x goes toward infinity is 0. 1 minus 0 is 1, and the natural log of 1 is 0. So this is indeterminate, but happily it's not just plain old indeterminate, it's indeterminate L'Hopital's. So now I can start applying L'Hopital's rule. So I'll have the natural log of y equals the limit as x approaches infinity. Now remember what L'Hopital's does is it says take the derivative of the numerator and the derivative of the denominator. So this is not the quotient rule. Now if you recall, the derivative of the natural log of u is 1 over u prime. So these are going to get pretty layered here. So let's go ahead and write out what that looks like. that will look like the derivative of the natural log of u is going to be 1 over u times the derivative of u. I'll write that as d dx. You can also write it as a prime if you would like. And the denominator is going to be the derivative of 1 over x. So again, let's do a quick review of what we have here. This is the derivative of the natural log of u is 1 over the argument times the derivative of the argument. In the denominator, I have the derivative of 1 over x. So let's go ahead. Next step is actually take those derivatives, and we're going to have to really simplify this a lot. On the left-hand side, I have the natural log of y. That's equal to the limit as x approaches infinity. And again, these are very layered. The derivative of 1 here is 0. The derivative of minus 2 over x, that would be the same as the derivative of 2x to the negative 1. I'll leave that negative there as well. So when I take that derivative, I bring the negative 1 down. Negative 1 times negative 2 is 2x. Decrease the exponent by 1 to the negative 2. So that's the derivative of the numerator. And then next, what I have here is the derivative of the denominator. So this is the same as x to the negative 1. So my derivative here would be negative 1x to the negative 2. And of course I can simplify this. Natural log of y is equal to the limit as x approaches infinity. So here in this term, I'm just going to leave this as is for now. And then for this piece, I can see that the x to the negative 2's cancel. 2 divided by negative 1 is going to be a negative 2. So I'm left with the natural log of y equals the limit as x approaches infinity of negative 2 over 1 minus 2 over x. Now as I take that limit, again, don't drop the left-hand side. As I take the limit, this piece goes to 0, and I'm left with negative 2 over 1, which is just negative 2. So I'm left with the natural log of y is equal to negative 2. So from here, I've taken my limit, so what I need to do now is to finish this. I know what the natural log of y is. I want to know what y is. Well, natural log of y, if you recall, is log base e of y equals negative 2. Now let me scoot up here. And then from here, what I can do is I can rewrite this in exponential form. So rewrite in exponential form. So that rewrite would be my base is e to the negative 2 is equal to y. So y is equal to e to the negative 2. That would mean y equals 1 over e squared. That's the limit of that. And so what that is telling me is the limit is 1 over e squared. That's going toward a particular value. So this converges. So this idea comes up a lot in this assignment. And how do you know when to use this idea of natural logs? Well, this is logarithmic differentiation, which is a technique you learned in Calc 1. Now we're applying it again in a slightly different manner. And I know I'm going to use this idea of the logs whenever I have a variable to a variable. So that's the key here. So again, if you have a problem that is a variable, that means like an x or an n to another x or an n, I'm going to use this idea of logs to get that exponent out and then work from there. Okay, so now we need to review some terminology. And we'll finally get to some problems from your homework set here pretty soon. But we kind of have to set the framework for everything before we go too far. Now this terminology is not just used for this section, we're using this for the entire unit. So the first thing we want to talk about is increasing. Well, increasing seems kind of like a no-brainer. Seems like we should be able to figure this out pretty simply. So increasing means always getting bigger. So we could go 1/2, 1, 3/2, 2. Basically here I'm increasing by 1/2 for each term. So this is called increasing. It means the next term is always larger than the current term. So next is greater than current. Notice no terms here are equal. We could also talk about decreasing, and it will be the same concept except in the opposite direction. So we could have 0, -1, -2, -3, etc. And for this one, our next term, which is going to be a sub n plus 1, is always going to be less than my current term. So next is always less than current. Okay. You'd think, well, we've covered everything. Everything either increases or decreases, but that's not quite true. It could also stay the same. So that's where we start with non-increasing. So non-increasing could be an example such as 0, -1, -1, -2, -2. And what this means is the next term is less than or equal to the current term. So the next is less than or equal to the current. So we have that equal sign. So we're saying, you know what? It's just not getting bigger. Non-increasing means it's not getting bigger. It could stay the same or just not get bigger. And of course, we're going to have non-decreasing to go along with that. So non-decreasing, this could be an example like 1, 1, 2, 2, 3, 3. And for this example, the next term, a sub n plus 1 is our next term, is greater than or equal to our current term. So next is greater than or equal to the current. We've also talked about bounded and monotonic, so let's include those in our list here. So monotonic, either non-increasing or non-decreasing. So I can have that unequal, the terms could be equal, but basically the idea here is it moves in one direction. And it might sit on the same value for a couple terms, but then it moves off in one direction. Okay, and our last one here was bounded. And bounded means, I guess we could write out a formal definition. It just basically means there's a finite lower value and a finite upper value, if I took the limit to find those. Okay, so again, all of these things are going to kind of come together to talk about one very important big idea. So this is an important theorem that we'll be using. And basically the theorem states a bounded monotonic sequence. So if I know it's bounded and I know it's monotonic, so every bounded monotonic sequence converges. So that's our big idea here. Converges. So let's look at an example that would kind of go along with that. So let's look at the sequence. Again, the sequence are these terms. 2 minus 1 over n equals 0 to infinity. So the terms here would be 1, 3/2, 5/3, 7/4, 9/5, etc. So we can see here what's going on. The denominators go increasing by 1, 1, 2, 3, 4, 5. The numerator is the sequence of odd integers, 1, 3, 5, 7, 9. So if we looked at these, we would say the terms are increasing. And they're not getting smaller. So we could look at this and say it's monotonic, so it has the same behavior. and it's monotonic increasing. And what we can see here then is that one part of this theorem, where the criteria have been met. So now we need to look at this and say, okay, now what about this bounded part? Well, it's bounded below by 1. So it's bounded at 1. And what's going on up here on the right? Well, if I took the limit here, the limit as n approaches infinity would be rewritten as a limit as x approaches infinity of 2 minus 1 over x. This would go towards 0, and so this would be bounded at 1 and 2. And again, I get that by looking at the limit as x approaches infinity of 2 minus 1 over x. Let's see if I can write this. 2 minus 1 over x. And that goes to 0, so this is equal to 2. So that's where that comes from. So the implication here is these terms converge, meaning they're going toward a particular value, and the particular value they're going towards is 2. So that's what we have here. I have monotonic increasing and I have bounded behavior. Now another type of sequence that we're going to find often is called an alternating sequence. So alternating sequences, we want to know, do they converge or diverge? And the answer is it depends. So we have to look at them individually. So I could look at one alternating sequence, and alternating means the values go positive, negative in the same repeating pattern. And I could look at them maybe at a quick graph. We're going to look at some obvious ones here. So if I looked at this first one, this particular alternating series is going to start positive and then go negative, positive, negative, positive, negative. Okay, and so we see this occurring. So we can tell very clearly that this converges to 0. Even though the terms are alternating, they're bouncing back and forth above and below 0, and they're getting closer and closer to 0. Let's look at this one that's going to alternate as well. And this one's going to bounce back and forth. And we can see that as these terms go back and forth, they're getting larger and larger. So we would say that this one diverges because the terms are getting larger and larger and going toward infinity. Okay, so that's an alternating sequence. In order to figure out what's going on here for sure, I'd have to actually take the limit and use some rules that I have coming up here. So the first particular type of sequence that I would like to work with today is called a geometric sequence. And this is very important. And some of this information is on your formula sheet about a geometric sequence, geometric series. So a geometric sequence is obtained by multiplying the previous term by a fixed constant. And this fixed constant is called the ratio, and it's represented by the letter R. So the form of this then is going to look like A times R to the n. So if you have anything that looks like A, where A is some constant, R is some ratio to a power, it's a geometric sequence. Now the rules here is R cannot equal 0. It could be positive or negative, but it can equal 0. A cannot equal 0, or the whole thing would go to 0. And it's any real number. It could be any real number. So A equals 0, cannot equal 0, and it's a real number. Now my rules here, it converges under certain circumstances, and it converges if R is between -1 and +1. And it diverges if my ratio is greater than 1, or if it's less than or equal to a -1. And I better fix this up here. There's no equal sign there, it's just a less than sign. Okay, so it converges if we're between -1, not inclusive, and 1 inclusive. And it diverges if I'm greater than 1 or I'm less than or equal to a -1. Sorry, let me clean that up again. Equal sign shouldn't be here either. There. So my equal signs go with diverge. So it'll diverge if r is equal to 1 or larger, or if r is less than or equal to a -1. So the limit then of these terms as n approaches infinity of a times r to the n are going to be equal to 0, 1, or the limit could not exist. These are our options. It's going to equal to 0 if the absolute value of r is less than 1. It's going to equal 1 if r is equal to 1. And it's going to not exist if r is less than or equal to a -1, or r is greater than 1. A few other characteristics. If r is greater than 0, then the geometric sequence a times r to the n is a monotonic sequence. If r is less than 0, then a times r to the n, that geometric sequence, oscillates. And oscillates means it bounces back and forth, kind of like this picture that we have up above, where I go above, below. And then of course we have to figure out whether it converges or diverges from there by looking at the value of r. Okay, so that is all the information on geometric sequence. And again, we use this information a lot. So let's go ahead and look at an example. Let's look at the geometric sequence 1 times 0.3 to the n. So this is a geometric sequence because it fits the form a times r to the n. A times r to the n. So from here, what I would do is identify a as 1, r is 0.3 or 0.3, and I can instantly look at that value of 0.3 and I could come up here and say, okay, this 0.3 is between -1 and 1. Therefore, it converges. Now, another thing that we could look at here is we could look at the absolute value of that. So the absolute value of 0.3 is just 0.3, of course, which is less than 1. And so that follows up here. Therefore, I'd have to say the limit as n approaches infinity, as my terms get larger and larger when I plug in n, so n equal 1, n equal 2, n equal 3, I'm going to have 1 times 0.3 to the n is going to be equal to 1. So that's what this information is telling us here. Okay, so we've talked a lot about kind of our foundation, and now we need to start working a bunch of problems. Actually, I think I have a mistake here. I just glanced up at our definition that I circled, and it says 0, but for some reason I wrote 1 down here. Okay, so let me explain why that's incorrect. So up here, our absolute value of r, 0.3, is less than 1, so that's this case right here. So my limit is going to be equal to 0, not 1. I'm not sure why I wrote 1. Okay, so now we get to start working some problems. Okay, so for this problem, we're working with a trig function, so that's always fun. What we want to do is find the limit of the following sequence, or determine that the sequence diverges. So let's go ahead and find the limit. We take the limit, again, we're using as n approaches infinity, of the inverse tangent of 18n over 18n plus 4. Now we can rewrite that then as the limit as x approaches infinity, because we're taking it from integer values to the real number system. Inverse tangent And whatever conclusion we can draw from the real number system, we can also draw for the integer system. So as I take my limit then, this piece, 18n over 18n plus 4, just this piece, not the whole limit, goes to 1 because the degree in the numerator is equal to the degree in the denominator, so I have 18 over 18, which equals 1. So what I'm looking at here then is the inverse tangent of 1. So you need to think about what this means. This means what angle in the interval, because remember we have restrictions here, from negative to positive pi over 2 has a tangent of 1. And of course you would know this because you have your unit circle memorized. Tangent is sine over cosine. So where in quadrants 4 or 1 do I have the same sine and cosine, same positive, same negative values? And that would be at pi over 4. Okay, so that would be my solution here is pi over 4. So it converges and it's going toward pi over 4. So that means as my terms get more and more out with n equal 1, n equal 10, and n equal 100, when I evaluate those, I'm getting closer and closer to pi over 4. Now this next one, we're trying to find the limit of a sequence again, and we're trying to determine whether it converges toward a particular value by finding a limit that's finite or 0, and then sequence diverges would be the other option. Now you're going to see some patterns here, but don't always rely on the patterns. Always do the work, don't just take a guess. So let's go ahead and start with the limit, and I'm just going to go to the real numbers right now. I'm not going to do the n first and then switch to x. I'll have 5 to the n plus 1. The plus 1 is in the exponent, plus 6 all over 5 to the n. Well, if I take my limit right now, I would get infinity over infinity, which is an indeterminate form, and it is indeterminate L'Hopital's, but I don't have my derivative of a to the u memorized, where a is the base is a constant. I have x to the second, but I don't have like 5 to the x. So I'm not going to say indeterminate L'Hopital's here. I'm going to say do more work, and I'm going to rewrite this. So I'm going to look at the limit as x approaches infinity, and I'm going to rewrite this as 5 to the n times 5 to the first plus 6 all over 5 to the n. I'm going to split that numerator up. So here I can clearly see that these cancel, and then I'm going to be left with the limit as x. I'm sorry, I switched to n's for some reason. These should have been x's here, because remember I was going to the real numbers right away, so I have to be consistent. X, x, and x. And this is x goes toward infinity. And I'm left with, after these canceled again, 5 to the first is 5, plus 6 over 5 to the x. So as x goes toward infinity, this numerator is fixed, so the denominator is increasing without bound. This is going towards 0, and the limit of a constant is a constant, so this limit is equal to 5. So this is looking at the terms of the sequence are getting closer and closer to 5. Now this next one, we're kind of doing the same thing. It says find the limit of the sequence and determine if it goes toward a particular value of finite limit or if it diverges. So right away, let's go ahead and rewrite this in terms of x, or real numbers. And then we have 5 to the x all over 5 to the x plus 3 to the x. Now what you cannot do here is separate the denominator. You can never separate the denominator. You can separate the numerator, but not the denominator. So if I take my limit here, that's going to be infinity over infinity, which is indeterminate. It's not an indeterminate L'Hopital's that I want to work with, because again, I don't remember my derivatives of 5 to the x. I remember x to the fifth derivative, but not 5 to the x. So I want to do more work here. Now for this type of problem, the do more work would be to divide through each term in this expression by 5 to the x. So if I do that, I'm going to be left with a limit as x approaches infinity. 5 to the x over 5 to the x is 1, plus 3 over 5 to the x. I'm going to rewrite this 3 to the x over 5 to the x as 3/5 quantity to the x. Now if I take my limit, what happens here is this term 3/5 to the x. This almost looks like that geometric sequence. This is going to go towards 0. Now, if it had been 5/3 to the x, that would be going toward infinity. That would be difference. So 3/5, it's less than 1. And because it's less than 1, this term is getting smaller and smaller and smaller as I go through and look at my subsequent terms in the sequence. So I'm left with 1 over 1 plus 0, which is 1. Now let's go ahead and look at this again real quick. This 3/5 quantity to the x, this fits the geometric sequence idea. And I can also look that it's bounded, has monotonic behavior, it's decreasing. So I could also say that it's going towards 0 because of that. But this looks like this a times r to the n. In this particular case, r is going to be 3/5, which is 0.6. And the absolute value of 0.6 is less than 1. Therefore, we know that this is converging or going toward a particular value. In this case, that's going towards 0. And if you scroll up and look at those notes again, we can see that real quick. And so that limit, if r is less than 1, is right here again, where we see that happening. Goes towards 0. So a lot of these things keep coming up over and over again in terms of usefulness, and the shortcut rules and being able to recognize a geometric sequence are important. Next problem that we're going to look at to try to determine whether the terms of the sequence are converging or diverging are going to involve factorials. So factorials are something that probably hasn't shown up for a while since you were looking at maybe something in your finite math class where we're talking about probability theory, perhaps in a stats class. But this exclamation point means factorial. So factorial means to decrease, sum means to add. We know the summation symbol means to add. Well, factorial means to multiply, but it means to multiply in a particular way. So n factorial is equal to n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. So we're looking at here now this limit as x approaches infinity of 16x plus 1 factorial all over 16x factorial. Now it's important that we see on the bottom, it's not the x that's factorial, it's the 16 times x that's the factorial. So if we take our limit right away, we can clearly see that this is going to be infinity over infinity. And then I don't want to take L'Hopital's rule because derivatives of factorials are something we've never talked about. So I want to do more work and rewrite this. So let's make those notes. So this is equal to infinity over infinity, which is indeterminate. And again, it is an indeterminate L'Hopital's, but we don't really have a way to work with factorials and derivatives right now. So what I will do here is more work, and the more work I'll do here is to rewrite it. So this would be the limit as x approaches infinity, and 16x plus 1. Okay, that's their factorial. Now the next term I'd multiply by 16x plus 1 minus 1. I'd go down by a term. So that would simplify to just 16x. And of course that would go down to 16x minus 1, 16x minus 2. And this is going to continue until we get down to 3 times 2 times 1, that same pattern. Well, this piece right here, 16x, 16x minus 1, etc., that is just 16x, and again, quantity factorial, not just the x factorial, but the 16x is factorial, so parentheses matter here. And in the denominator, I have 16x, quantity factorial. So what ends up happening is these cancel, and I'm just left with the limit as x approaches infinity of 16x plus 1. And the denominator is just equal to 1 in this case. So this is equal to infinity. So what I have here is the sequence diverges. So factorials will show up here. And factorials are kind of fun to work with. It's not something that we've seen recently, so you might have to refresh your memory a little bit on those. Our next one, we're kind of jumping back to a trig function, but we do need to remember our unit circle for sure here and our trig derivatives. So let's have a look. Let's take the limit, and again we'll rewrite this as x right away, as x approaches infinity of x times the sine of 16 over x. Well, if I take that limit, I get infinity because this piece goes to infinity. Now this piece in the parentheses, 16 over x, goes to 0, and the sine of 0 is 0. So this is an indeterminate form. This is not indeterminate L'Hopital's, this is just indeterminate, which means I need to rewrite it. So we're going to use that trick that we've used previously. I'm going to take the x that's in the numerator and rewrite it as 1 over x in the denominator. So now when I take the limit, I get indeterminate, 0 over 0, which is indeterminate, but more importantly, it's indeterminate L'Hopital's. Now because this is indeterminate L'Hopital's, in this case, I can take the derivative. Some of our previous ones, I had to just rewrite using a different technique. So the derivative in the denominator is negative 1 over x squared. So the derivative of x to the negative 1 in the denominator is negative 1 x to the negative 2, which is negative 1 over x squared. And the derivative of the sine is the cosine of 16 over x times the derivative of 16 over x, which would be negative 16 over x squared. Okay, so these are Calc 1 derivatives, so hopefully that you remember those derivatives and how to use the chain rule. So as I simplify here, I have the negative and the negative that cancel, but I'm left with this 16. Okay, so the negative 1 over x squareds cancel, but I'm left with a 16. So when I rewrite this, I have the limit as x approaches infinity of 16 times the cosine of 16 over x. Now again, as x goes toward infinity, this piece, not the whole thing, but this piece goes towards 0. So I have 16 times the cosine is 0. Cosine of 0 is 1, so I'm left with 16 here. So this does go toward, these terms are getting closer and closer to 16 as my values for n get larger and larger and larger. So for this next problem, we're still using trig functions here, but we're asked to plot this one. So it says plot a graph of the sequence and then determine if the sequence goes toward a particular value if the limit exists or if it diverges. So in plotting this, that might give us kind of an idea of what's going on here. So to plot this, we're going to have to choose some points, and then when we choose those points, what ends up happening from there is I should be able to evaluate that cosine function, but we're going to have to choose our points wisely. So let's go ahead and start with n equals 0. For n equals 0, that would be the cosine of 0, and the cosine of 0 is equal to 1. So we'll put 1 up here, negative 1 down here, and here's n equal 1. Now if I plug in values like, say, like pi over 2 up in here, I'm going to have pi over 2 here. I'll end up with pi squared over 8, and that's not anything I know the cosine of. So we have to kind of choose these wisely. We want to choose integer values. So we already did n equals 0. Now think about n equal 1. n equal 1 is pi over 4. I want to choose kind of more of the quadrantial angles. So I want to choose n equal 2. And for n equal 2, I'd get 2 pi over 4, which is pi over 2. And the cosine for that is 0. Now let's go ahead and keep going. Cosine of 3 pi over 4, it's the second quadrant, so I know it's negative. Let's look at the cosine of 4 pi over 4. That's the cosine of pi, which is negative 1. So I already can predict what this is going to look like because I know the behavior of the cosine graph. It's going to look something like this. Now, because I'm plotting individual points, it'll look something more like this, because it's not a continuous, because I'm plotting these little integer values. So right away I can see a couple of things. This graph is bouncing back and forth between negative 1 and 1. So negative 1 and 1, I'm bounded. So this is oscillating. So again, that means going back and forth between two values. And it doesn't have a limit because it oscillates. So because the limit doesn't exist, the sequence diverges. So this one I can tell pretty quickly just from the graph. Now I could try and take a limit, and if I did take a limit here, what would happen is I would have the cosine of infinity, and that's not anything I can evaluate because it oscillates, again, goes back and forth between -1 and 1. It doesn't settle on a particular value. Our next problem is an application problem, and it's a really interesting one. So what we have is we're taking a certain pain medication, I think they're referring to aspirin here, as a preventative measure for heart disease. Suppose a person takes 80 milligrams of the medication every 6 hours. Assume also that the medication has a half-life of 6 hours. So the 80 milligrams you take, let's say at noon, in 6 hours at 6 p.m., only 40 milligrams is left in your bloodstream. And then you'll take another 80 milligrams at 6 p.m., and then again that builds up again. So that's kind of the pattern that we're following here. So what we want to do, first of all, is find a recurrent relationship. So that's part A here. So we want to be able to write a sequence on how we're going to figure out how much is in your blood after you take enough doses, kind of like what's that maintenance level. So what we can do here is we can call this D sub n. So we usually call our sequences A sub n. So what this will look like then is our next dose, again this is recursive, is what I'm used to calling it, is equal to our previous dose, obviously, and it says it's the half-life in every 6 hours, so half of our previous dose plus our new dose, which is 80. So this is our current D sub n, or sorry, this is our current D sub n plus 1, is based on half of the previous dose plus another 80 milligrams. So what happens is that medication builds up in your bloodstream, and part B is, what does it build up to be? So what we want to do is determine the limit of the sequence. And you could graph this, but I think we can also do this by hand pretty easily as well. So determine the limit of the sequence. So when we start talking about the limit here, I'm going to take the limit of x goes to infinity of d sub x plus 1. I'm going to take the limit of both sides. I can't just take the limit of one side. Is equal to the limit as x approaches infinity of the right hand side, and that would be 1/2 d sub n plus 80. Well, both of these limits are equal to some finite value L, because I can't overload my blood if I follow the instructions with this particular medication. So it doesn't matter if it's my previous dose or my current dose, after everything, again following the instructions, goes toward a particular value, it's bounded. So each of these is equal to some finite value L. So that's where we're going to start with here. So the limit of a constant is a constant. So here I have L equals, the limit of a constant is a constant here as well, 1/2 L plus 80. So to solve for L, to figure out what that finite value is, I would subtract 1/2 L from both sides. So L minus 1/2 L is 1/2 L equals 80, and then multiply both sides through by 2, and I get L is equal 160. So 160 milligrams is, if I take my medication as prescribed, the level that will be built up in my blood and to help me maintain my preventative heart disease. So that's 160 milligrams. Now if you were to graph this, what it would look like it's leveling out at about 160. Okay, so that's a nice little application of those. This is another neat application problem. This one has to do with investing instead of medication. We have a person that begins a savings plan in which they deposit $110 at the beginning of each month, and the account earns 9% interest annually. So now if it earns 9% interest annually, what ends up happening is I can take that 9% and divide it by 12, and I would get that 0.75%. So again, if you take that 9 divided by 12, that's that 0.75% there. To clarify, on the first day of each month, the bank adds 0.75% of the current balance as interest, and then he deposits $110. So that order is important here. Let B sub n be the balance in the account after the nth deposit. Our initial balance is 0. So complete parts A through C. Well, I'll tell you what parts A through C are. So part A is write the first 5 terms of the sequence. So we're going to definitely need a calculator here. So our initial they give us as 0. So there's 0 to begin with. So that is B sub 0 is equal to 0. Now B sub 1 is going to be equal to $110 because there's no interest rate. So if I wanted to write it out, I would take 0 times my interest rate and then add the 110. Now I can't just multiply it by 0.75. I need to multiply it by 0.75%, which would be 0.0075. Okay, and then I add in the $110. So at the beginning of month 1, after the first deposit, I have $110. Now B2 then, I'd start with 110 times 0.0075. So that's the amount of interest that I earn on that first account. And then I add another 110. So actually I want to sneak another 110 in here. So I have the 110 from above, and then I'm going to add my interest 0.0075, and then I'll add another 110. So this is from B1, and this is 10% of B1, and this is my new deposit. So if we plug everything in for that, I get $220, and I get 0.825, but I'm going to round this to the nearest cent because we're using money here, and so I have 220.83. Let's go ahead and look at B sub 3. So to start, I'm going to have 220.83, so that's my B sub 2, plus 220.83 times 0.0075, again that's that B2, plus another $110 is my new value. So let's see what we get for that one. So when I plug this in, I get 332.486, but that would round to 0.49 then. We want the first 5 terms, so I have the first 4 so far. We can see our pattern here. So if we were to use a spreadsheet like we did on some previous homework units, we could really set this up to calculate these very quickly. Be kind of fun. So again, that's our B3 plus another 110 is our new. So we can see how quickly that this account grows. So let's go ahead and plug that in and see what we get. So plugging that in, I get $444 plus, and I should say 0.983 cents, and that would round to 0.98. So these are my first 5 terms, 1, 2, 3, 4, 5. So those are the first 5 terms of a sequence. Now, the second part, part B, they would like us to find a recurrent relationship. So if I want to write that recursive sequence, what I want to do is start to try to predict what's happening here. Well, these are like terms. They both have the 332.49. These are the like terms as well. So I have these like terms. So if you think about factoring out the 332.49, I'd be left with 1 plus 0.0075, which would be 332.49 times 1.0075. And then of course the plus 110 here. So this 332.49 is our recursive part because that came from B3. So B4 is equal to B3 times 1.0075 plus 110. But I need to kind of write this out generically. So I would go B sub n plus 1 is equal to 1.0075 B sub n plus 110. So that's the recursive relationship. Now part C is asking, determine how many months are needed to reach a balance of $52 to $100. And this, maybe you're saving up for something right here, like a four-wheeler or something. I guess would be around $5,200 used. And that'd be a pretty nice used car too. Okay, so how could we figure that out? Okay, so we're going to answer that problem by creating a spreadsheet. So I'll have month, and I'm going to be using our recurring formula that we had before. So my months, I'm not sure how many months this is going to take to get to that particular balance. So I'm going to maybe fill in, I don't know, 75 or 100. And if that's not enough, we can always easily add more by just copying and pasting. So let's take this and fill this down to maybe 75. Actually, I went way too far there. Okay, so now let's write our formula up here. And we start with a zero balance, so there's no formula to write for the first month. But then my second month, this is going to be equal to, so I use the equal sign, of course, our previous month. So I just click on the cell. I don't want to type in the letter or the number 0. And I take that times 1.0075 plus the amount that I invested was 110. And hit enter, and that's my value there. So I'm getting this from this value right here. So this is my recursive. So if you wanted to maybe not use the B sub 4, let's use the one underneath. I'm using this formula right here. So 1.0075 times the previous balance is the previous cell plus 110. Okay, so now what we can do is we can use our fill handle here to copy that formula, and then we can go ahead and round these to the nearest cent, which isn't a huge deal, but we want to go ahead and round these to 2 places. Okay, and so we want 5,200. So if we scroll down here, 5,200 right here is at month number 41. So that would be my answer there using the spreadsheet. And I'll paste that spreadsheet in so we can see where that came from. Now you could also do that by hand, but I don't think it would be very fun. So the spreadsheet is really helpful there. So again, I didn't take the spreadsheet from 0 months. I kind of just took a screenshot of this bottom part. But 5,200 is reached. Our balance is reached right here at 41 months. So that's where that comes from. As usual, if you have any questions while you're working, please let me know. I'm always happy to help. Good luck.